Let's move on to the issue of the Gram Schmidt process. Okay. So what's the issue here? The issue is in life we like lines to be perpendicular to each other. This situation is a lot easier for us to handle than two vectors that perhaps make some kind of arbitrary angle between the two of them. The question is, if you are dealing with some kind of an engineering situation or physical situation where your vectors are like this, can you create another set that is related to this set in the sense that we are going to describe, but their angles are turned into 90 degrees, kind of forcing a system to be opened up, like you have such a thing in a certain manner, a certain constrained manner. We want to open them up so that the angle becomes 90 degrees. Of course, with respect to 2, it's not a big issue. The topic comes up in any number of dimensions, and really its application is when you have many vectors in high dimensions and you want to kind of force them to bloom up and open up, as opposed to just a situation like this where you could have 3 vectors making arbitrary angles between themselves, as opposed to having like a corner where all the angles are 90 degrees. So Gram Schmidt process is a way of opening things up. There are plenty of choices you have there, and we have to kind of constrain it. Like if I got 2 vectors here and say open this thing up, and you say, okay, don't use these, use these 2 over here. So I want to open these guys up. I don't want to go somewhere else and do something altogether new. So the process that we have, we are going to call these things by some vectors. For example, we're going to call them V1 and V2, or say V1 and V2 and V3. And after we open them up, we are going to perhaps call them in a certain order, P1 and a P2, or say P1 and or let's say this is P1 and P2, P3, or some style. So we're using P's to indicate the result of our process where things are perpendicular. So P's are going to be perpendicular, and the V's are the original, which could be at arbitrary angle. What's the trick that we want to apply? Well, in a sense, we want span up whatever we are creating to match span up whatever we're having at the beginning. So we are not leaving the space and going to our backyard and doing something there. Rather, we want to be relevant to what we are starting with. So span of P1 has to be same as the span of V1. Span of P1 and P2 has to be same as the span of V1 and V2. Span of P1, P2, P3 has to be same as the span of V1, V2, V3. So both of them are describing the same space. It's just that one set is nicer looking than the other set. So here is requirements that we have in our mind. Span of P1 has to be same as the span of V1. So we number our vectors in some way that are significant to us, and we get going after that. So how many vectors you got, step by step we are going to do our constructions so that the space that is described by these vectors, that is not changed. It's just that your building blocks are changed. The trick that we are going to apply is based on the idea of projections that we learned last time. Let me just quickly remind you what that one was. So we will use before I get down in the formulas, let me tell you what it is all about. Let me redraw the picture. So suppose I have this V1 and this V2. I want to force them open. That is, I want to create P1 and this guy will be P2. So okay, take V2, drop perpendicular and draw this one to this perpendicular line. Okay, this V2 can be resolved into two components. One is this one. One is this one. This is what we learned last time. We called it, what did we call that? This, the first blue one. Let me let me call this vector T, or let me put it capital T. This one was projection of V2, so let's call T is equal to projection of V2 on V1. Like cast the shadow of V2 on V1. This is the shadow. Well, what should I do to V2 utilizing this shadow, so that whatever is left is perpendicular to V1? I can think about V2 as two components, T and N. Is that right? V2 is the vector T plus the vector N. Now, what should I do to V2 so that N will be surviving member? So, yeah, exactly. Just take V2, shave off this shadow off of it. Whatever is left is just a normal component. And that normal component, that's what we are going to call P2. Okay? As simple as that. So, so we set, in some manner we get started with our first important vector. We're going to call it V1, and we just copy it through. We don't have to do anything there. P1 is just same as V1. P2 is, we say, take the next vector, V2. From that, subtract its shadow on the first vector. So we say projection of V1, projection of V2 on the very first one, which by now is just called P1. Okay, P2 is V2 minus projection of V2 on P1. I need a new page, so let me get started and do this thing again there. So let's just write the formula for this. So again, we have V1, V2, and then we open this up to P1, P2. Have a question? Yes. So projection of V2 on P1. I'm going to write that again. Okay? Is that clear? Okay. So so we say P1 is same as V1. P2 is V2 minus projection of V2 on P1. So that is, now do you remember what was the formula for this? We learned last time V2 P1 over P1 P1 P1. Okay, looks a bit crowded, but that's first perhaps crowded formula we got. So here's our formula. P2 is V2 minus that thing. Remember, this is, whatever it is in direction of P1, and P1 itself is just a copy of V1. what is after this? We need to do two things. One is to practice this idea, and the other one is what if I got a lot more vectors than just two, and that's where things become interesting. Most of the examples you have at most 3 vectors, but in applications these things are done on situations where there could be tens or hundreds of vectors. So let's just write that too, and then I come back to the practice. So suppose I have so the intimation here is that we have a 3-dimensional situation. So we actually have like X, Y, Z, and let me see if I can give the correct impression of what is it that we, however you draw these things in 3 dimension. Somebody misunderstands it, so let's see. Okay, we want to open them up and essentially recover our X, Y, Z axis out of our vectors. And so our first vector P1 is just copy of our V1. We don't have to do anything. To force V2 open, it's going to create our P2 for us. After we have opened this, we go after V3. V3, we cast its shadow on the existing vectors that we have created. Remove those shadows. Whatever is left is going to be our P3. So the formalism is going to go like this. P1 is just a copy of V1. P2 is whatever V2 was minus projection of V2 on P1. P3 is going to be V3 minus whatever shadow it casts on the existing perpendicular set that we already have. Whatever shadow it casts on V1, we remove it so it doesn't duplicate this direction. Whatever shadow it casts on P2, we remove that so it doesn't have any component going in that direction. So the only direction left for him to go is going to be straight up perpendicular to both. So that's going to be projection of the last guy minus, projection of last guy on the very first of these vectors we have created, and then projection of again that vector on second member that we have created. So on the right hand side, the subtractions that we do are the projections on the portion of the system we have already created, and then we go step by step, and if you had more, we just list more of these things. Now let me just go ahead and write the formula for this one too. So P1 is same as V1. P2, good practice for you to just rattle it off. What should I write here? Times P1. P3 minus what? P1, 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 and then what else? Minus? Most common mistake here is students take V2 here. If you take V2, it doesn't work. Your resulting vectors are not perpendicular. It has to be built up against the existing perpendicular vectors, not the original whatever you got. That has V2 has no significance anymore. It's just P2 that. So this is what we call Gram Schmidt. Gram Schmidt process is a basis of certain ideas in calculations in engineering or numerical work. Before we go any further, let me say that it is not a stable process. So if you are going to become an engineer later on, you have to know ahead of time that there is a little bit of a fine print next to this thing. It's not really, so I don't want you to become a CEO of a Toyota and build a car on this and then come back and say, well, it's not working or something. So there is something about it that doesn't work in high dimension. The errors build up and things get out of whack. Things look nice in these formulas that we write, but when you want to do stuff, you operate in a world of limited resources. So these numbers are always done on a computer. Computers have limited precision. They don't have infinite precision into them. And so they just chop off numbers at some place. And an issue with any kind of mathematical formula is that if you have these chopped off numbers snowballing on top of each other, would things get out of hand? Would the final result be anything close to what you were expecting? And it's a tricky issue. One famous case of that is something that came up during the U.S.-Iraq war, that they had these Patriot missiles presumably hitting against Iraqi Scud missiles. So everybody is celebrating that these are actually hitting those missiles up in the air. It turned out none of them were hitting any missiles. On the other side, they were just exploding up in the air. Everybody was celebrating. But there was a problem with the finite precision of the timer on these equipments, just not keeping the time right, so things weren't just working right. So there is always an issue that the numbers that you work with are coming with error and have finite precision on your machines, and things that look nice on a piece of paper might not turn out to be that way on the actual situation. So let's just go ahead and take a look at one example. Since we are doing these things by hand and we are keeping all the numbers accurately as they are, there is no danger now. But there could be somewhere else. Well, we might as well take the very last of these. These examples are a little bit contrived, with all numbers having such a nice looks to them and such. But anyway, we have these three vectors. The question is, it's saying, so this is problem 50. Find perpendicular vectors P1, P2, P3 such that span of P1, P2, span of V1, V2, and the span of all three of them are the same. So it is telling us, okay, go ahead, make the other three vectors and watch out to stay within this prescription. Okay, that's what is requested in this problem. So who is P1? 1, 1, 1. Who is P2? So it is V2 minus V2 P1, 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 P1. What is meant by this here? That's a dot product, is that right? So V2 R vector minus R vector 1, 1, 0, let me squeeze them here, times R divided by, I hope my handwriting is readable, times what? 1, 1, 1. That's our P2. Let's just do that. So it's 1, 1 0. Do the numerator for me. What is the numerator? Just 2. Denominator, say it again, 3 times 1 1 1. So you have 1 1 0, 2/3 2/3 2/3. So what is that? 1/3 1/3 minus 2/3. Is that right? That's our P2. So what we got out of this is that P2 now most engineers like to write 1/3 as 0.33, and that's the beginning of the trouble. So these numbers not being so nasty, we just keep them accurate as they are, as opposed to running for our calculator. So right now I just write it 1 1 minus 2. I factor the 3 out. That makes my life a little bit easier. Now I go for next round. P3. Who's P3? Say V3 minus copies of this type. P3, V3, P1, 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 and V3, P2, 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 P2. Now a word of advice: if you have found P1 and then P2, would double of P2 or triple of P2 just work as well? So that's right, is that? It's if this is perpendicular to the first one, you're making it a little bit longer or shorter, still perpendicular to the first one. So you might use that feature to make your life easier. Like if you try to use this, chances are quite high that over here you're going to make some arithmetic mistake. But what's a better vector to use, and actually resulting in the same thing? This would be better to use than a P2 itself. Why? First of all, a multiple of a vector is as good of a perpendicular to the other ones as the original one was. The shadows are not going to be any different. The advantage is that you don't have to live with the misery of dealing with all those fractional numbers, round off, etc. So that is actually preferred. So let's listen to that advice. Let's see if our life gets any better. P3 was 1 0 0 minus V3. So let's write 1 0 0 P1 P1 1 1 1 1 1 1 1 1 1 1 1. My handwriting becoming sloppy now, but this is not friendly environment to write. Minus V3 1 0 0. So instead of P2, what's a good thing to use? 1 negative 2. Notice if I multiply this by a number, that by a number, this one by a number, that one by that number, all of them are going to cancel each other out. So it's up to me. If I want to multiply all of them by 10, that's fine. If I want to multiply them by 100, that's all fine. Here, what makes sense to do is to multiply by 3. So that I just extract this number, P2, 1 1 minus 2, and that is going to be a huge lifesaver there. Okay, so you either use it like this and live with all the fraction stuff, or clean it out, use this one. If you want to call that N2 or N3, that's fine. P3. Okay, help me out here. Numerator is 1. Denominator 3. Numerator of this one 1. Denominator say it again. 6. 1 times 1. 1 times 1. Minus 2 times minus 2. That's going to be 1 times 1. Plus 1 times 1. Plus minus 2 times minus 2 makes 6. 6 of 1. 1 minus 2. So P3 is 1, 0, 0 minus, well, 1/3, 1/3, 1/3 minus 1/6, 1/6, if you wish, minus 2/6 of minus 2/3, minus, let me just write it, minus 2/6. So I take 1 minus 1/3 minus 6. Second component 0 minus 1/3 minus 6. Third component 0 minus 1/3 minus minus, and this is 1/3. So what is this one? This one minus 1/2, is that right? And this one 0. So P3 became 1/2 of 1 minus 1, 0. So let's write down our final answer. P1 was just copy of what we had, which was 1, 1, 1. P2 official algorithm starts with 1/3 of, but really 1, 1 minus 2 is just as good and actually nicer. P3 official algorithm ends up with 1/2 of, but really this one would be nicer. What do we do at this stage? We're doing a lot of arithmetic, so you might as well check. And that's where it breaks down in engineering algorithm. You go through this process, you use your calculator, you do stuff, you come at the end, you check, it doesn't check. And the reason is that the round off has built up so much that you're just producing quantities that don't make good sense. What is a check? Well, what is a check? You tell me, what is a check? That P1 dot P2 has to be 0. And again, the multiples don't count. What is really important is the ratio of the items inside. So what is the dot of these two? So P1, so that factor of 1/3, we are pulling it outside. P1, P3, that is, check that 1, 1, 1, dotted with 1 minus 1, 0. There's a factor of 1/2 in front of it, but that doesn't count either. When you multiply, what do you get? 0. And P2, P3, you have 1/3 and 1/2. Again, that they don't count. 1, 1 minus 2 dotted with 1 minus 1, 0. That's again 0. So you make sure that you check your stuff. Okay then. So you finish up the section on